Okay, let's start. So what do you guys think about this one? Quick predictions.
It's going to diverge.
Think diverge? Why?
Because regardless of whether you, I mean, you can test for absolute convergence first, right? You get n over basically 3n, so you get 1/3. So that's not going to go to anything. And then if you even take the limit of it with the
You're
alternative
thinking too
series,
far. Like you've already sort of said the answer. The limit of this is not 0. Limit of that is going to be 1/3 as n approaches infinity. So yeah, that's going to diverge right away by the test for divergence. Problem 1, this is problem 2. So 1a, all you have to just say is that the limit as n approaches infinity of n over 3n plus 1 is equal to 1/3, which is not 0, diverges. Right, test for divergence, again, it's always something you kind of always want to imagine in the beginning, because if it works out, it's the easiest one to see, and you don't have to do anything. Yeah, what about B? What do you think in B? Yes?
For like A, it diverges, but like, why doesn't it like converge conditionally?
Because the limit does not go to 0. To be able to converge, it has to go to 0 in either case.
Okay.
Yeah, that's a general thing. Whether it's alternating or not is irrelevant. Like if the limit does not go to 0.
But like if that would converge, then it could diverge.
It could diverge with absolute values. Like the canonical example is comparing 1 over n to -1. That, right? This one converges conditionally while that one diverges. Because if you take the absolute value of this one, you get that one, which is a divergent p series. But if you put the negative signs back, it actually converges by the alternating series test. However, it is the case that the limit of 1 over n is 0.
Yeah.
So the only reason why you'd even think to check conditional is because the limit goes to 0. But once the limit is not 0, you don't have to check anything. There's no saving it. So it has to approach 0. There has to come a point where what you're adding is like adding nothing, essentially, for there to be an answer. But here, it's like, no matter how far off we go to infinity, it's like we're adding a magnitude that's always like at least 1/3 in absolute value. It's not going to converge to any sum.
So
The terms are too big.
1 over n diverges
Yes.
because of the p series test?
Yeah, a bunch
So-
of tests. You can even say, this is a famous series, you can call it harmonic. You can say it's harmonic.
So
That's
can
what
something only converge conditionally if it diverges?
absolutely.
Converge conditionally means with absolute values it does not converge, but without it, it does.
But not in terms of like the divergence test?
No, the divergence test tells you about divergence right off the bat. There's nothing else to check. If
Okay.
it diverges according to the divergence test, it diverges.
Okay.
There's no saving. There's no conditional or absolute
Okay.
conversion.
But if it diverges anywhere else, you should also check the alternating
Yeah,
series.
but if it diverges by some other test, you would check it without the absolute values. Yeah, but the test for divergence applies to all series and it eliminates all possibilities of convergence, whether you're putting absolute values or not. So what about this one? What do you think?
It's geometric.
It's geometric. Right? So this guy here, that 3 to the 2n is really like 9 to the end. Right? So this really looks like -1 to the n times 5 over 9 to the end. Now the thing about geometric is whenever it converges absolutely, but you could throw in absolute values if you want, but it's really optional at this point. So it's geometric. So this is geometric. And since the r in this case is 5 over 9, it's less than 1 in absolute value, it converges. Absolutely. So when a geometric series converges, it converges absolutely.
Do we
Right?
understand?
And why? Because if I threw absolute values around this, the idea is if I actually took the time to do that, and then I would get this guy, the same rule applies. My R would still be 5/9, and I'd get it to converge anyway. Right? So geometric series, they converge absolutely once they converge. So that's also something you don't have to test. C, what do you think?
Would
Yeah.
it converge conditionally?
So your intuition is converge conditionally?
Mhm.
How so?
Well, if you do I used the comparison test, so for absolute, I put it in absolute value bars and then I
Okay,
had.
so if you do, so you check absolute first.
Yeah.
Right, now in the case where something might converge and you're not exactly sure, you do want to, I should probably, I don't know if I ever wrote that down, but I should, you should be aware of that. If convergence is suspected, but it's not totally obvious how or why or when or where it will converge, then you always want to check absolute convergence first. Right, because if it converges absolutely, you don't have to check conditionally. But if you know it converges conditionally, you might still have to check that it's absolute. So it could potentially, not checking this first could double the amount of work you have to do. Then, if that doesn't work, check conditional convergence. If absolute convergence does not work. And third, if neither of the above work, it's divergent. Right? So you look at this series, you realize that the limit of the thing goes to 0, so it's possible for it to converge, but we're not sure. So what we would first do is check absolute. So we're going to consider the series with the absolute values around it, which is just pretty much going to be 1 over 3n plus 1. So now we're looking at that series, and your intuition tells you what?
Well, I compared it to 1 over 3n,
Mhm.
and then.
What would the comparison be here? Which way would the inequality sign go? So if you're
1 over
comparing
3.
1 over 3n plus 1 to 1 over 3n, who's bigger?
1 over 3n. No, plus 1. Wait, 1 over. Isn't it 1 over 3n because it's.
When the denominator is smaller, the
Yeah.
fraction is bigger.
Mhm.
So this guy is actually
Bigger.
bigger.
Mhm. And then I used I guess the P series test. So the
Yeah,
n
but does the comparison theorem apply here? What can you tell me about this guy, if I put a series?
If,
1 over 3 to the n, by the way, I
yeah,
can factor out a third, and that's 1 over n.
yeah, that was
So
my check, and then it diverges.
it diverges. So if the bigger guy diverges, what can you say about the comparison?
It doesn't.
It doesn't apply. There's no conclusion that can be made from a direct comparison. So
Yeah,
what's
and
the
then
option?
you use the alternating series test like that.
Not yet. You still have to argue that this will diverge
Okay.
in this case. So instead, direct comparison doesn't work because the bigger guy diverges, and you can't make a conclusion on that. So in the case where you want to use a comparison theorem, but it just doesn't apply, you use limit comparison. Right? Because in limit comparison, remember, the order actually doesn't matter. But if you take a n equals your 1/3n plus 1, and your bn to be the series you want to compare it to, then what you do is you look at the limit of the quotient, right? And it turns out that in this case, that's going to be 1, which is greater than 0, and this means both diverge. So we have to make, before we even check conditional, we have to be certain that absolute does not work. We have to be able to make a conclusion here. But the direct comparison doesn't work because the inequality sign is not pointing the right way. So whenever direct comparison would be nice for it to work, but it just doesn't work because of the way the inequality is pointing, you want to use the limit comparison, and you can make a conclusion based on that, usually, hopefully. So yeah, divide this by that, take the limit, you'll actually get 1, which is greater than 0. And once you get an answer that's greater than 0, that's a constant that's greater than 0, it means both series will do the same thing. Since I know this diverges because it's harmonic, it implies that this will have to diverge as well. So we don't have absolute convergence, and now we check conditional. So C continued. So now we're going to check conditional convergence. So now we're looking at the original series, put back the negative signs there, and what can we say? It was 0.
That f is decreasing and the limit equals 0.
Therefore?
So, it converges conditionally by the alternating series
Right.
test.
So you notice that this is alternating. And an equals 1/3n plus 1 is decreasing, and limit of an equals 0. This implies, let's call this S. S converges. And you'd have to put conditionally here because with absolute value signs it didn't converge. So in this case it converges conditionally by the alternating series test. So this diverges, this was converges absolutely, this one converges conditionally. What do you think about this one, D?
You can do a couple of different things with
Sure. What's the first thing?
this. I mean, the first thing that I jumped to is you could look at it and recognize that's basically geometric and it's 2/2 to the n, pretty much, and that's 1. Or you could do a limit test, that's divergence, or.
Yeah, how do you say it's geometric though? Because that +1 in the denominator.
Well, so I guess, I don't know, maybe not.
Yeah, the +1 is going to sort of mess up the geometry. If the +1 was in the top, you could do that, because then you could divide into each. But yeah, there's something even more basic than that here.
You could just do test for divergence.
Test for divergence. The biggest guy in the top and bottom is 2 to the n, so essentially the ratio is, the limit is 1. That diverges. What if this were 3 to the n? What would happen in that case? Let's say I had 2 to the n over 3 to the n plus 1. That limit goes to 0. How would you tackle that?
Might be easiest in the ratio test at that point, probably.
Ratio test could work. There's probably something more elementary. This is kind of, you compare it to that. I would just do a comparison really. Either the limit comparison, because this we know is geometric.
Right.
And that has the ratio, the r is 2/3. So I know this converges, and I can do like a comparison test Which way would the thing point?
Just 3n on the bottom is bigger, because the +1 makes it denominator.
So this is bigger and that converges, so I could use a direct comparison test here. So directly compare with a geometric series. If for example the top was the 3n and the bottom was a 2n,
Ratio test.
you guys are thinking too complicated. You guys are going all the way down to the bottom of the table.
Test for divergence.
Test for divergence, that goes off to infinity, right? 3 to the n is much bigger than 2 to the n. You could also realize that if you compare that with a geometric series, it would be a divergent geometric series. And if you take the limit of the ratio, that would actually go to 1, and so you can do that. Right, so exponentials are kind of like polynomials in the fact that the bigger the base is, like the one function will overwhelm another. So 3 to the n is going to be huge compared to 2 to the n at infinity, and so it's top heavy, it's going to go off to infinity, whereas the opposite is true here. And you can use comparison test or just realizing that the limits, in the case where the exponentials are the same, the limits, or the top is bigger, the limit's going to go off to non-zero, and the opposite happens here. So you didn't really need anything as complicated as the ratio test here. Simpler means would have done it. So that diverges, that was easy. What about part E? So it's just like with integrals. If you're faced with a random integral on a test, you don't immediately start throwing partial fractions at it, right, or trig substitution. You kind of look for an easier way out. Could a regular U substitution work? Or could I just expand and simplify and use the power rule, right? That's always what you want to look for first. So one of the first things you want to test for is the test for divergence. It's always going to be, or at this point it should be, easy for you to look at something and know if that limit's going to 0 or not. So that's probably going to be one of the first things I'm going to look for. If not, I'm probably going to try to do a comparison second, right? Because we know certain forms of how things behave. So if I can compare it to something, so if something has like powers, I can try to compare it to a geometric series. If something is rational, I can try to compare it to some sort of P series. And that's kind of probably where I would go next. Otherwise, if something is too complicated, like part E, notice that this one, yeah, there's a term that kind of reminds me of a geometric, but there's also a factorial, so that messes up the comparison there, right? So here I have exponentials and factorials and a polynomial. That's kind of really messy. That might need something really tough to deal with it, and something like here is where I would start to think the ratio test. I wouldn't think it here. These functions are way too simple to need something that huge. So E, it's not easily comparable to a P series. It's not easily comparable to a geometric series. The limit does go to 0 because we know factorials grow a lot faster than exponentials. So here's where I would do something like the ratio test. But just having that thought process of knowing that you're going from easier to harder and you're just using patterns to figure out what you might want to do it's very useful, and it gets you through the problems a lot quicker so you can focus on the harder things. So if your functions are relatively simple, try to do like a test for divergence or a comparison. It's when things start getting complicated and you have different functions mixed together, that's when you need something a little bit more sophisticated, like a ratio test or a root test or something better than that. So towards the bottom of the table, those are really like the guys you pull out when you really have to. So in this case, I would try the ratio test. So what does the ratio test say we should do?
Absolute value.
So we're going to look at the absolute value.
AK plus 1.
Right, or an plus 1, I'm using n here, over an, and what are we looking for?
The limit.
We're looking for the limit as n approaches infinity of that. And as long as that is, how do we make conclusions here?
The limit is less than 1, it converges absolutely. But
If it's greater than 1, it will diverge, and if it's equal to 1, there's no conclusion that could be made. So you'd have to try something else. But in this case, it's definitely going to be one or the other, because we can see that the numerator and denominator, they're in two different orders. It's definitely going to be a conclusive one here. So yeah, we're looking at that limit, and based on its size, we can see what happens. So we look at the limit of, I'm going to go here and replace all n's with n plus 1s. 2 to the n plus 1. This would be 2n plus 3 over n plus 1 factorial. Multiply by its reciprocal, which is the same as division. So that's going to be n factorial over 2 to the n times 2n plus 1. So we're looking at that guy. Now again, that one's slightly messy, so we want to simplify, and usually it's nice, as I said, one thing you often want to do is just to group similar functions together, because we have multiplication here, the order doesn't matter. So I can put the similar functions together. So 2 to the n plus 1 and the 2 to the n are similar, I put those together. The rational functions are going to be similar, so 2n plus 3 over 2n plus 1, put those together, and the factorials I'm going to put together. It's easier to see the answer that way. Right? And so now we can start looking at how these limits are going to behave. So in this case, this cancels that, so I'm just left with a 2. What can you tell me about this guy?
It's gonna go to 1.
It's going to go to 1 because the top and bottom powers are the same. So I can essentially replace that with a 1. And this guy?
0.
No, n plus 1.
Right, this is n factorial over, this is n plus 1 times n factorial. So that cancels. And so now I have the limit of 2 over n plus 1 in absolute values, and what's that? That's 0, which is less than 1 always. Right, it's less than 1, and so this means converges absolutely. Yeah.
When you added the plus ones to the original equation, how'd you get 2n plus 3?
Because here, if I replace my n with n plus 1, the 2 would distribute. So it'll be 2n plus 2 plus the 1. Yeah. So that's what happened here. Yeah, so this was really 2n plus 1 plus 1. Other questions? Okay, let's look at the last one, F. To infinity of minus 1 n ln n over n. Okay, so what are you thinking here?
Can you see that it's like greater than 1 over n? Or, yeah.
I was thinking the integral test.
Come again?
The integral test? Because then if you, like for the absolute value,
Yeah.
u is ln of n, and then that cancels with the n on the bottom, and then you're left with infinity to 1 of u du, so then it diverges absolutely.
Mm-hmm.
And then you can do like another test, like I did the alternating series to see that it converges conditionally.
Mm-hmm. So we can test absolute first, and there are a couple ways we can do this one. Yeah, the integral test is probably what I would have seen first, but a comparison actually does also work. So we can test absolute convergence to see if that would work. So you'd have a couple options here. One is the integral test. One way you'd see that it's the integral test is because the thing looks like it's easily integrable if you use a substitution. So if you say your an is ln n over n, notice that this is decreasing, positive, and continuous, which you have to check and mention if you're going to use the integral test. And so pretty much in that case, you can find the integral of ln x over x dx. And so that would pretty much be the integral of u du if your u is ln x. And so that gives you ln x squared over 2 from 1 to infinity, which of course diverges. You could also do a comparison. Notice that ln n over n is bigger than 1 over n. Which means the series of ln n over n diverges by comparison. So both options are valid here. Not always that you'll see both of these could work, but in this case you could do them. And here you can just say for a large n, because ln is not always bigger than 1, but of course there comes a point where it's always bigger than 1. So absolute convergence doesn't work, so now you want to check conditional. So now you look at an and notice that ln n over n is decreasing and the limit equals 0. Is it obvious to you that this is decreasing? Because ln grows a lot slower than n. You could find a derivative if you want and show that it's always negative. You could also just realize that if you look at y equals x versus y equals ln, the ln is always actually going to be smaller. Pretty much all the time. So the fact that that's decreasing because the denominator is growing a lot faster than the numerator is something you could verify in tons of ways. But once it's decreasing and the limit is 0, this means that the series ln n over n converges conditionally. By the alternating series test. So I think that was a hefty amount of practice to actually go through just practicing the intuition that you want to work with and sort of the levels you want to take things. You always want to start off with like test for divergence or a comparison of some sort for things that look simple. You really use like the heavy hitters like the ratio test for things that are really complicated that mix multiple kinds of functions together. And it's really hard to get a grasp on what's going on. That's when you try to talk about ratio test, root test, something similar to that. Another time you'll always use the ratio test is for problems like these. So when you want to find the radius of convergence, it turns out that the ratio test actually has an interval built into it. It talks about when the absolute value of something is less than 1, which branches out into an interval. And so that's why it's very useful for this. So whenever you see a radius of convergence problem, there are several techniques you could use on this, but for the typical problem in Cal 2, it's always going to be ratio test. It's just how it's going to work out. But technically, you could kind of try to apply any of the convergence tests in general to figure out when it's going to work. So move on to these. 2, part A. So once you realize you're after an interval or radius of convergence, you're gonna use the ratio test. So our L in this case, we're going to equal to the limit as n, which is infinity of an plus 1 over an. The important part here is that n is the variable that you're using here, so your x might get left over, which allows you to solve for the range of x's. So you're pretty much going to go through and again replace all the n's with n plus 1s. So this is just the limit n plus 1, well n plus 2 times x plus 2 to the n plus 1 over n plus 4 squared times the reciprocal. And again, I group similar things together, so here's n plus 2 over n plus 1. Compare that to n plus 3 squared over n plus 4 squared, compared to x plus 2 to the n plus 1 over x plus 2 to the n. These guys will both go to 1 because they're a ratio of polynomials where the degree of the top and the bottom are the same. This one here cancels that one here, and so the limit just ends up being x plus 2. So we want to find the interval of convergence, that's where it's converged. We need L to be less than 1 for convergence. This means we need x plus 2 to be less than 1. So now that immediately tells you the radius of convergence. Right? Because remember that if we have x minus x naught less than r, that number r is your radius of convergence. So immediately here I can say the radius of convergence is 1. And now for the interval of convergence. Basically now I'm going to rewrite this as an interval. So if that's that, it means it branches out into this. By the rule of absolute values, I can subtract 2 from both sides. So I'm considering now the interval from minus 3 to minus 1. And so now we test the endpoints. So if your x is equal to minus 3, what you do is you plug that into the original series. So we're going to go back here, plug in x equals minus 3. And so that would give us minus 1 to the n plus 1 over n plus 3 squared, which converges or diverges.
Converges conditionally.
Converges conditionally by the alt series test. And if I plug in minus 1 for x, go and plug into that series, I would just get n plus 1 over n plus 3 squared, which converges or diverges? Diverges. By comparison, right?
Yeah.
With 1 over n. Just look at the highest power, so the highest power here is n, the highest power down there would be n squared, so it's going to behave like 1 over n. And either a direct comparison or a limit comparison will give you that conclusion. And so we know that it converges here and diverges there.
So does it not matter if it's just conditional convergence?
No, we don't care. Any kind of convergence is good enough here because it's happening within the context of a ratio test. So overall, we know that any convergence is ultimately going to be absolute.
So how does x equals -3 it converges conditionally? Like, how do you know that?
Oh, we did a test. So
So you the alternating.
yeah, so without the signs here, it diverges because the
The bottom's
divergent
bigger.
because the bottom is only 1 degree bigger. So that means it's comparable to a divergent p series. So I put the sign back. I notice that this here is decreasing and the limit is 0. So it is a problem like what we were doing in problem 1. But in the context of this question, you don't have to like go through it all and write it out. You just need to state the result. At this point, I would already have tested that you have the ability to actually make a proper conclusion here. So here you can just say it. Like you don't have to actually go through it. But you are actually doing a convergence test from the table here. So this here is an alternating series and it converges because the limit of this term is 0 and it's decreasing. And without the negative sign, it's not alternating, so I would compare it with 1 over n and it would diverge. So this would mean, so this is 2 part A, continue. This would mean that my interval of convergence is going to be, it converges at -3, but it does not at -1. So as long as we're in that interval, this series will converge absolutely. Which, by the way, it tells us we can do calculus on it, provided we're in this interval. Outside of this interval, calculus won't work, because the sums won't behave. Which leads us to the final problem here, 2b. Same thing for this series. Find the interval of convergence and the radius of convergence. So, again, use the ratio test, always what we're going to use in this context. So we're going to compute L, which is the limit of, replace all n's with n plus 1s, multiply by the reciprocal, group things together so we can see them easier. This guy's going to go off to 1. This guy cancels that guy, so I'm going to be left with a third. And this guy would be x minus 2. Just x minus 2. So this means for convergence, we need 1/3 x minus 2 to be less than 1, which means x minus 2 must be less than 3 by multiplying both sides by 3. That immediately gives you the radius of convergence. And now for IOC, minus 2. This would break open into this. Add 2 to both sides. Now we get that. Now I'm going to test endpoints. So my x equals minus 1, plug that into the original. That would be the sum of minus 3 to the n over n plus 2 times 3 to the n, which basically just becomes minus 1 to the n over n plus 2, converges conditionally by alternating series test. If I plug in x equals 5, my series would become 3 to the n over n plus 2 divided by 3 to the n, those cancel, so that's just a series of 1 over n plus 2 diverges. It's basically harmonic. This means your IOC. That's your interval of convergence, this is your radius of convergence. Any questions on that? So problems like these would be in the first part of the test. So you kind of really have to know how to do this. The other thing with series is when we're trying to apply what we know about power series, and that will be in part 2 of the test. So then I should give you an example like that. I'll give you a couple of examples like that. Let f of x equals 1 over 1 plus 2x. 1. Find the first 4 terms of its Maclaurin series. Use 1 to find f of 0.01 with an error less than 0.001. So technically this one doesn't require any calculus, the one I'm going to ask you about would, but this is just a nice little segue problem. And then I'll give you another problem that you can expect a problem of that type to be on. But yeah, given that function, how would you find its Maclaurin series?
And turn it into 1 plus x, sort of thing. 1 plus x or 1 minus x?
1 minus.
1 minus, what do you know about 1 minus?
We know that.
1 over 1 minus x is?
Oh, the series
Power.
of x, yeah.
Because that's geometric. That works when your x is less than 1 in absolute values. This guy converges absolutely to that guy because it's geometric. Your a is 1, your r is x, and if your r is less than 1 in absolute value, it converges to a over 1 minus r. And so that's actually a series, just x to the n. So this guy, you're going to try to piggyback off this one. So you probably write it like that. And so now, you just, if this x changes to minus 2x, you'll just replace that x with minus 2x. So it's just going to be minus 2x to the n. Or in other words, we can kind of rewrite this here. Minus 1 to the n times 2 to the n. And it says find the first 4 terms.
And from 0 to
So you're just going to plug in n equals 0, 1, 2, and 3. It's asks us for a specific value. Well, after the first 4 terms, we're going to plug this in and then evaluate it at that value. So plug n equals 0, I would just get 1, right? Plus, plug in n equals 1, I would get minus 2x. Plug in n equals 2, I would have plus 4x squared. Plug in n equals 3, I would have minus 8x cubed. 1, 2, 3, 4. Those are my 4 terms. And of course it goes plus that. But that's my first 4 terms. So now what we want is, so that was part 8, to find the Maclaurin series, the first 4 terms. And we're just really using the fact that we know that what 1 over 1 minus x looks like. And b, so this means that f of 0.01 would be approximately, I'm just going to replace x with 0.01. By the way, this is f of 1 over 100, right? So that's going to be 1 minus 2 over 100 plus 4 over 10,000 minus 8 over 1, 2, 3, 4, 5, 6, 8 over 1,000,000. Okay, so what's your approximation? Start looking at this guy. What is this guy equal to?
Zero, 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 zero.
0.00.
0, 4.
Right? This one is even worse. That's way, it's 0.1, 2, 3, 4, 5, 8. Okay. Now, how good do we want to be? This guy here is actually going to be 0.002, right?
I think just 0 2, right?
0.2. Yeah, because it's over 100.02. Now, what is the point of thinking about it that way?
You can find a sum.
Yeah, so we only need the first 3 to get an error less than, or sorry, no, the first 2.
First 2. This guy here is already less than 0.001, which means that the sum of the previous terms is going to be good enough to be that accurate. So, since the magnitude of, let's call this A0, A1, A2. Since the magnitude of A2 is already less than 0.001, A0 plus A1 is an approximation. That fits the error bound by, well, what are we using here?
The alternating series approximation.
It's called the alternating series approximation theorem. And basically that theorem says the magnitude of any term tells you how good the sum of the previous terms is in relation to the actual answer. And so f of 0.01, I can think of it as approximately equal to this guy, which is going to be 98 over 100, or roughly 0.98, and that fits the desired accuracy. Okay, let's do something a little bit stronger. So the problem on the test is going to be far more similar to this one. It will be in the optional section, but it's, I mean, in the grand scheme of things, you might prefer to do this as opposed to something else. So here, f of x is given as e to the minus x to the fourth. And one, find first 4 terms of its series. And that's just a Taylor series centered at 0, or the power series centered at 0. And use 1 to approximate this guy, the integral from 0 to 1/2 of f of x dx with an error So here we're given a function. You can't really find the general antiderivative of that, but you can approximate it on any interval by a multitude of techniques, but in this case we are going to use the techniques of the Maclaurin series. using the Maclaurin series. Okay, let's start off with 1. So what would you do? This is something that we know.
Isn't e of x,
Right, so that should have memorized. This is x to the n over n factorial. And approaches 0 to infinity. I'm sure it's memorized by Monday next week. It will be fun. So e to the x, sine x, cosine x, and 1 over x, these are power series that you should have memorized. And basically you're going to either find other Maclaurin series by actually just substituting x values into one of those to get a new function, or you can figure them out by differentiating or integrating. So if you know the power series for 1 over 1 minus x, I could easily ask you for what is the power series for ln of 1 minus x. So you just integrate that power series into a certain interval. But yeah, we know that e to the x is that. This means that e to the minus x to the 4th would just be me plugging in minus x to the 4th into that. And I will notice here that that is actually an alternating series when it plugs in. This means for the first 4 terms, e to the minus x to the 4th. Yeah, it said the first 4 terms. So I'm literally just going to plug in n equals 0, 1, 2, 3. So if I plug in n equals 0, I get 1, minus plug in n equals 1, I get x to the 4th, plus plug in n equals 2, I get x to the 8th over 2 factorial, which is just 2, minus plug in n equals 3, x to the 12 over 3 factorial. Plus dot dot dot. Or this is 1 minus x to the 4th plus x to the 8th over 2 minus x to the 12th over 6. So that's the first 4 terms of its Maclaurin series. And this means we can move on to part 2. The integral from 0 to 1/2 of this function is going to be approximately equal to the integral from 0 to 1/2 of this function. That's just the power rule. So we're going to have x minus x to the 5th over 5 plus x to the 9 over 18 minus x to the 13 over, what's 6 times 13? So this is going to be 1/2 plus 1 over 5 times 2 to the 5th plus 1 over 18 times 2 to the 9 minus 1 over 6 times 13 times 2 to the 13. So this guy might look big enough. Who is that? What is that?
32.
Times 5.
Which gives us?
40? It's 160.
Yeah.
That's 1 over 160. Is that less than this? No,
No.
right? Because I need, that's 1/1000, so I need at least 1000 here. And I'm pretty sure that this is gonna be more than 1000. 2 to the 9, 18, that's definitely gonna be more than 1000. So that's my approximation here. So this means, I don't know, can we check that to make sure, like, for satisfaction? The integral from 0 to 1/2 of f of x dx is going to be approximately equal to 1/2 minus 1/60.
Yeah, it's 9,216.
9,216, yeah. So, with an error less than 0.001 by the alternating series approximation theorem.
So quick question.
Yeah,
Let's say you had an error that was, let's say way more, or way smaller than that, right? And potentially less than the last term that we've gotten from the previous one. I don't think this is the type of thing that we would get in a problem either from your test or from another test like this. But is there a way to tell before you do the integral how many terms you're probably gonna need for that error, or do you just have to?
yeah, start here and solve for n.
Okay.
Right, so the idea is if you want to plug in, well, you integrate this, right? So if you look at something like this guy, if you look at the integral of e to the minus x to the
Okay, I
fourth,
see.
in general, you'd have to do minus 1 to the n, x to the 4n plus 1 over 4n plus 1 n factorial. And what you kind of do is, if you evaluate that between 0 and 1/2, you're going to get like minus 1 to the n of 2 to the 4n plus 1 times 4n plus 1 times n factorial, and you just set that less than the error that you want and solve for n.
Okay, cool.
And then you can know, well, if you want this error, you can just pick this many n's.
Right. Okay, cool.
In this case, that's not an option. I wouldn't ask you to do anything like that. Because here they pretty much tell you only do 4 terms. The answer is going to be within there.
Right.
Yeah, but in general, if the question were, how many terms would you need to ensure this error? That's how you do it. And this problem might be difficult to actually solve directly, but just start guessing and checking. Plug in n equals 10 and see, oh, well, that's more than enough, and you can kind of just dwindle down.
Cool.
Okay, yeah, so that's basically it. In the review, was there any other issues that you guys are having in terms of topics that were covered?
Is this what we would cover on Wednesday? Or,
Sure. I mean, you guys want to leave now?
oh,
Are we gonna have a review on Wednesday?
It's up to you. Are there issues that you guys would want to cover that we haven't spoken about? Because we only do with series so far. But you have to remember everything from before. Like integrating stuff, all your integration techniques, word problems, finding arc length, all that stuff. So what I could do is I can probably give you some ways to, because I'm not going to create a mock final, but I can kind of tell you how to create your own based on stuff that's already available. And then you can sort of go through those and just kind of looking through it, maybe trying a few, you'll be able to tell me if you'd want to meet on Wednesday or not. But since Calculus 2 is pretty much the same anywhere you go, you can kind of use stuff from my old college. So you guys can look this up, maybe Google it on your phones or something to make sure you can find the right site, but if you can try this. It'll be a good guide if you kind of construct things this way. You might have to do a little bit of shifting to fit the compulsory section versus optional section as the way I described it, but this is a very good base to start with. So try this. So Google. So it's just for extra practice. Say C, C, N, Y, math. And you can go to courses when you see that. So you'll see a list of courses. Among them, you will see Math 202 and Math 203. Now this is Calc 2, and this is Calc 3. But the weird thing at CCNY is they actually do series in Calc 3, not in Calc 2. So if you want to practice the series problems, you'd have to look into Calc 3. But if you want to practice pretty much everything else, look into Calc 2. And so what you can do is you can actually construct finals from here. So when you click on each of these, you can see past final exams. They'd have a bunch of exams here.
Search CCNY courses and it comes right up.
Yeah.
Search all three
Oh,
courses.
well, I put math. I don't know if other departments have similar things.
CCNY math courses,
Yeah.
all three words together, then
Yeah.
it comes right up.
And look up past final exams. They have a list of final exams for each of these courses. And so here's how you would kind of construct a mock final.
There's like 5 years of them.
Yeah, there's like 5 years worth of them so that's like 10 practice finals essentially. If you can get through all of them, great. You'd be in excellent shape. But if you can get through 2 or 3 and you're pretty solid, and you know, or if you're just looking through them and you're like, I don't remember how to do that, that might be something you want to go over on Wednesday. You guys can email me. But construct the finals in this way. Like so. Okay, so in any Math 202 final, replace anything with volumes of revolution. So that's where you might see things that it mentions like the disk method or the washer method or find the volume obtained by rotating this around that. With series problems from Math 203. So I'll give you a couple examples of this. So a possible final is, and you can mix and match them however you want, just make sure you can. A couple examples of this is you can go to Math 202, fall 2014, and then replace problem 4 with Math 203, fall 2017, problems 6 and 7, 8. Yeah, and you have a good approximation for what your final would look like if you did that. Another option is, so you pretty much can mix and match semesters, and you're just putting in a series problem where there are no series problems and eliminating volume problems where there are volume problems. So another nice approximation would be something like, start out with Math 202, fall 2013, and replace and these were kind of symmetric, and replace problem 4 with Math 203's spring 17, problem 6 and 7. Another thing you want to know how to do is in terms of conic sections, like I said, I'm not going to ask you for things like foci and directrix. And so for conics, focus on simplifying so that you can figure out what kind of conic you're looking at. Is it a hyperbola? Is it a circle? Is it an ellipse? And sketching. Make sure you know how to sketch those. So if it asks you for anything else that's weird, like, oh, find the foci of this, like, just ignore that problem. Or if it asks you, find the angle of rotation of this, we don't care. Just know how to recognize what conic you're looking at and do a general sketch of it. But yeah, you can just do that. You can take all the Math 202 files, go through them, eliminate all the volume problems, and anything that asks you excessive about conics. Throw in a series problem from a Cal 2 exam, and you have like a mock final to work on. And if anything in that seems too far back, you don't really remember, it's going to be a good practice run. So you might have to shift the arrangement of problems a little bit if you really want to get into looking like the final. So go over what I told you our final would look like, and how many problems is in the compulsory section versus the optional section, and the problem types that are in each section. You can rearrange your problems to fit that nicer if you really want to practice it.
So the exam's the full 2 hours?
Yeah, 2 hours, 15 minutes, roughly.
Is there any way we're gonna get to fix your test board? Like,
Well, not today, but you can see it before. Yes. I mean, I'm here all week, so I should be finishing grading that by Friday.
And then, speaking of Friday, that's when all the homework is due, right?
Friday's also when all the homework is due. But between now and then, I have 3 finals, so my focus needs to be more on my other classes. So I'm not going to grade your test for until like Thursday night, Friday morning kind of thing.
So come Friday afternoon.
Yeah. So yeah, we'll stop there. On Friday, one of the finals is Friday. I think in that mass email I sent you about the final schedule, you'll see when my final on Friday is. So obviously you'd have to come outside of that window as well. Okay. All right, we'll stop there.
So, question.